Welcome to the chapter 5 of this MOOC, in which we will analyze a simple data logger based on the STEVAL STWIN1B board and using a simple USART connection through the ST-Link. Regarding the MOOC timeline, we will now implement, or not really implement, we will see that we provide in this MOOC a prepared project, but also in the slide set the complete workflow to rebuild this project from scratch. So this simple data logger will be used in the two next chapters, the chapter 6 and 7, to review the other options that are available in the NanoEdge AI Studio tool to import the data in a given project. This chapter is divided in three parts. The first part will consist in unzipping the input prepared project that is available in the materials section of this MOOC. And we will review quickly what are the minimal components that are needed to implement a data logger, notably SPI interface to communicate with the sensor and a USART configuration to output the logs. Then we will review in the STM32 CubeID project the needed functions for the data logging, so filling a buffer with the sensor data and output it in the USART connection. And finally, we will build and run the data logger and retrieve the data on the PC. The opening should take a few seconds, so feel free to pause the video until the project is open. And we will go to the A to Z peripheral list. You can see here that very few components are enabled, very few are needed, in fact. The most important one is, of course, the USART. This specific USART 2 is the one that is connecting to the ST-Link. It's going through the ST-Link, so that's why we will use this one and output the USART transmission through the ST-Link directly on the PC through a virtual COM port. Another important component in our situation is the timer 6 that will be used to simulate the output data rate of the sensor, since we will implement a data logger in pooling mode. So we will ask regularly to the sensor to give us new data. Usually on sensor you are using the push mode, in which an interrupt occurs from the sensor to say that new data is available. But to be as simple as possible, we will use a pooling mode here, based on the timer 6. So the configuration that is set here will be overwritten in the source code. And the SPI 3 will be used to communicate with the sensor itself. And that's all we need, in fact, to start. So normally in the step in the slide set, you will have to generate the code. Here it has been already generated, so we will open directly the CubeID project to review the additional source code that is needed, that is not handled by the CubeMX. Because remember that the CubeMX does not handle the external peripheral, the actually connected element, only the configuration of the internal MCU. So let's launch the CubeID environment. Again, feel free to pause the video until you get to the same position as me, since it can take a few seconds. We can close the CubeMX project now. So the easiest way to launch the CubeID project, to open it, is to double-click on the .project file. So the project is being imported in the CubeID workspace and is now available for us. So you will see in the full presentation of the CubeMX project which files are automatically generated. In this case, it's almost all of them except some parts of the main.c. All other files are automatically generated, and these specific drivers for the sensor have been manually added also, because it's not handled directly in CubeMX. So regarding the data logger itself, we have defined a specific define called enable logger. So all the code that is between this if-def definition have been added to add the specific data logger feature. So let's now review each of them to understand what is needed for this data logger feature. So the first step that is not handled by the CubeMX and must be added by the user is getting the value from the sensor. For that, we need a specific include file that contains the register and the API to request the value from the sensor, and an initialization function that is the meminit function here. So this function uses two other functions. So this is really specific to the sensor. It configures the output data rate and some other variables. So we can see here that the output data rate of the sensor is 1600 Hertz. The next step is to log this data into the buffer. The buffer that has a specific size, and this is defined at the very beginning. So here we selected a buffer size of 512, which is a power of 2, as is suggested in the generic rules. Our accelerometers output 3 values because it's a 3-axis sensor. So the full signal size will be the buffer size multiplied by the axis number. And the actual buffer is a global variable, which is defined here, of the size of the signal size. So basically, our program will first initialize the sensor. Since we are in pooling mode, there is an additional timer to be configured that will be aligned on the sensor frequency. So it will expire, so an interrupt from the timer will occur based on the sensor output data rate. That's very specific. Most usually you work in push mode, so an interrupt from the sensor occurred, and then you release it to retrieve the value. And so the basic application will generally call the log function. Here we added, it's more convenient to have a state machine. So when the application starts, we are in inactive state. So the app state can be inactive or log. The default one is inactive, and by the press of the button, an interrupt is raised that changes this app state to log state. So by default, the application will just print on the USART, we will see how, press the user button to start data logging. So let's see quickly how the press of the button is changing the states. So let's go back just a second in the CubeMX project. In the CubeMX project, we defined a specific GPIO, which is this one, so the one on which the user button is linked. And when the rising edge is detected on this GPIO, then an interrupt is triggered. And the callback that manages this interrupt is this callback. If it is the actual, the correct GPIO, the correct pin, then we switch between inactive and log mode. Another cosmetic, let's say, implementation here is the use of the LED. So the green LED, you can see here that on each tick increment, the LED is toggled. So just to keep in mind that the LED period will change whether we are in log mode or inactive mode. So when we are logging in log mode, the LED will blink fast, and where we are in inactive mode, it will blink slowly. That's just to have a visual indicator of which mode we are in. So finally, when we enter the application, let's go back to the main loop. Let's say now that we have switched to the log state, we will then call the log function. Okay, let's go like this. No. The log function will call two functions. First, fill the buffer. We separated the two, filling the buffer and printing it, transmitting it to the USART, because in the application, in the last chapter, we will use the same input program to run, and it's easier to have both separated. So the fill buffer function will fill this log user buffers, which is the global variable, the array we saw before, of this size, with this size of input data sensor. So let's go to this function, and we can see here the calls, direct calls to the accelerometer to get each axis and store it in the buffer that is provided as an argument. And finally, we will print this buffer. And to print this buffer, we will use simply the printf function. You can see that if we have reached the size of the signal, then we will put a new line character just after the sensor sample. Otherwise, we will log the sample in the buffer. And the printf, we have to modify also something so that it outputs the data to the USART. This is done by redefining a specific function that is the _write function. This function is called by printf. It has a default implementation and it's defined as weak, so you can overwrite the function. And we will overwrite it by just calling the HAL USART transmit function. So instead of using the printf to output to the default output, in fact, we will output to the USART. So now let's test our project, but before that we need to enable the code for the datalogger. So let's go in properties and declare this preprocessor instruction. So in C++ settings, in tool settings, you have the list of the preprocessor here. So now it's enabled and we can build the project. In the meantime, let's plug our board. So the ST-Link is already connected here. We will power it up. So the compilation is done and we can flash the board. So once it's connected, since we are in a debug session, it will stop on the first instruction. So nothing is running now. If we resume the execution, we can see that the green LED is blinking slowly. So it means that the application is waiting for our input. And let's verify that using TeraTerm. So TeraTerm is a tool to listen on a specific serial port. The serial port should be not the default one. So to determine which one it is hired, you can test all the available ones, but you can also go in the device manager. Let's see that right now. So to check which COM number is the one we want to use, you have to open the device manager and look for the virtual COM port, or ST-Link virtual COM port. You can see here that it's number 16. If I unplug the board, so let's first stop my execution. So I stop the debugging, and I unplug the ST-Link. So you can see here that the virtual COM port disappeared also. If I plug it again, it will come back. Here. So let's listen to this COM port using the TeraTerm. And we have to adapt also the serial port speed. So the serial port speed is defined in the CubeMX project. If you go to the USART2 settings, you can see here that it is defined to 230,000 kilobit per second. So we have to adapt it here also. And we can see here that the application is logging the same information. Press the user button to start data logging. And if we press the user button, which is located here, just above the black one is the reset button, the white just above is the user button. Then you can see the sensor data logged into the virtual COM port. And you can see also that the green LED is blinking faster than when in active mode. If I press again the user button, we'll go back in active mode. So this is it for this data logging project. You are now equipped to achieve the next two chapters, chapter 6 and 7, where we will use this data logger to review the other import options that are offered by the NanoEdge AI Studio tool. So the import from USART, from USB, and the import from file. One additional point before closing this chapter. The version of the datalogger we just reviewed is using an additional timer to limit the access to the sensor to its actual output data rate. But in fact, you have two archives provided in the materials section. So the first one is the one we just reviewed, the datalogger USART ST-Link. And the second one is as an additional postfix, which is a sensor IT. And this one uses the sensor interrupt instead. And the steps to switch to this version is also included in the full slide set. So we have now functional datalogger. Let's see how to use it in the NanoEdge AI Studio tool.